Okay. Last time I introduced modules over commutative rings. Today I'll talk about linear maps, but before that, that gives few more. Before that, that gives few more definitions for modules. They are, of course, part of linear algebra, standard linear algebra as well. So first, let's talk about dimension. But so last time I talked about the free module over something, but there is some kind of reverse definition, something to be free if there exists a basis for it. So consider, so let's start with commutative ring continuity. Let R be a commutative ring continuity. And V be an R module. And we say that V is free if it has a basis, if and if we say it's finite dimensional, if it has a finite basis, and we say that V is finite dimensional, if it has a finite basis. And if this basis is finite, so if E1 to En is a basis of V, we write maybe I should write it this way, and then I don't know, something like that. It depends on a basis, but there is a theorem that says that the number of elements in a basis is unique. So let's formulate the theorem. It's not that easy to prove it, so I just will formulate it. So some theorem. So theorem says that the dimension is uniquely determined. So start with a basis with a ring. A finite dimension. Be a finite. A finite. Now, R module and E and V be basis of E and F be basis of V. Then dimensions of respect to V is equal to dimension with respect to F. I think this theorem is called Schwarz, not this theorem, but a lemma that directly from which directly follows this thing in linear algebra is called Schwarz lemma. So we denote the unique dimension. We denote the unique dimension by the dimension of V. So what does this tell is that if we find one basis, we are sure that all bases have the same number of elements. Okay, so let's give examples. So start with Rn. What's the dimension? So letter D. RD. Okay, it's different with unity, and M and N are natural numbers. What's the dimension of Rn? It's N. Why? Because what is the basis of Rn? What's the standard basis of the space of tuples? Yeah, it has a basis given by the unit vectors. So AI equals 0, 0, 1 on the it position, 0, 0. Sorry, from 1 to n. 1 to n. Okay. N. Okay. Dimension of space of matrices. What's the dimension of space of n by n matrices? It's n times n. M times n. Because there are m rows and columns, so n times n independent coefficients in some sense. So because I don't know what they called unit matrices, the matrices EIJ for one, E from 1 to M and G from 1 to N. So AIJ is 0 except that IJ component. Where it is 1. So it's everywhere, a matrix everywhere 0, just one single element is 1. Like these vectors here, but matrices. Matrices, it has form a basis. It's form a basis of M. What's the dimension of the zero vector space? Zero, it has no basis. So because the empty space is the basis of it. Because empty space is empty space is a basis of it, of the zero vector space. Zero, not zero R module. And the space of polynomials, what's the dimension? R fix is the space of polynomials. It's infinity, but it has a basis. So I didn't define the basis, which is infinite, but because it has infinite it has an infinite basis. So the basis is 1, x, x squared, and so on. Okay. I will not try that, but it might happen that on a vector space, usually things have bases, but on a commutative ring, there may be modules that don't have bases. But we're only with those that have bases. Okay, span. I didn't talk about span last time. I talked about span the whole space, but that's an important thing as well. So once again, let R be a commutative ring with unity. Again, let R be a commutative ring with unity. V be an R module. And take some elements. Let's say V1, V M are in V. And we denote the span of by so the span. So span of these vectors, of this set of vectors V1, Vn, is by definition the space of all linear combinations. So this is the space lambda 1 V1 plus space lambda 1 V1 plus n Vn, where lambda 1 to lambda n are in R. So this is the span. Equivalently, this is the O vectors in V. So this is the set of O vectors let's go with double in V that have such representation. So there exists lambda 1, lambda n in R such that W is equal to this thing here. Let's go with sum of E from 1 to n, lambda I Vi. Okay. So just to remind that last time we found, last time I gave some matrix and wanted to find its image, and it was equivalent to find the span of its vector rows. I think was it vector rows or maybe vector column vectors. No, it was the span of the column vectors of a matrix is the image of that matrix. So I would just do a remark here. The image of a matrix is the span of its column vector, the span of its column vectors. Okay, and I forgot to say that this is a vector subspace. So maybe put it here, but also remark span is this is a subspace of the it's a submodule, sorry, it's a submodule. So if we have a finite set of vectors, we can combine them and get the space they occupy. For example, in 3D, if we have two vectors and they will span a plane. So yeah, let me draw some picture. So we are like here and have two vectors, V1 and V2, and we can make the whole plane they span. So it's like that. I don't know. I'm very bad at drawing in 3D, but something. Okay, I have not drawn a plane, but I think you understand. Two vectors span a plane and cuts the whole space. Maybe if they are linearly dependent, there will be just a single line. And this works not only for over real numbers, but other spaces as well. Okay. The span. Now, some interesting example, some other example for span. For instance, let's say, consider the set of 1x squared, which is, for example, rational polynomials, doesn't matter. It's a space of this kind of polynomials. And the span of S is the set of all polynomials of that nature. So this would be A1 times 1 plus A1 x plus a2x squared. So this is denoted. This is the space of polynomial of degree up to 2. So quadratic polynomials. So quadratic polynomials. Quadratic polynomials. So this is an example of finite dimensional subspace of an infinite dimensional space. All polynomials are infinite dimensional space. Okay. Yeah, this kind of we'll do spans when we have but something like that when we have, for example, spaces of multi-vectors or forms where we can split into 2 vectors, 3 vectors, and they have span by different kind of basis elements. Okay, so now I'll go to linear maps. So this topic of today, the main topic, linear maps. Unfortunately, I have to go through a lot of topics of linear algebra in short order. So we start again, as always, with some commutative ring with unity. So let R be a commutative ring with unity. And V and W are V and W are R modules. And F is a function from V to W. We say that F is a linear map just homo. R modules if the following 2 conditions are satisfied. So it should be homomorphisms of groups. So for all V1 and V2 in V, we have F of V1 operation if in V. So we add these 2 vectors as elements of V. And the result is in W, so we have to add them in W. F of V1 plus with respect to the operation in W of F of V2. And it should, the scalar should go outside somewhere. So for any scalar in R, in any vector V in the first module, we have F of lambda multiplied by, let's say, the operation in V times the vector V is the same as multiplying lambda, but this time in W of F times V. So it should respect those operations. So yeah, this is a linear map, and we denote the space of all linear maps by the set of homomorphisms. So this notation is used. Sometimes this is when it's clear from the context, the subscript is not used. So sometimes, or things of something like that. Sometimes you can see not H home but L of like linear maps, or sometimes like L of VW. I suppose I'll use this notation or this when R is clear from the context. Maybe this, because okay. Let's give some examples. Okay, the most, what's the most trivial linear map when this are equal? Yeah. And the zero map as well. So, okay, first example with the zero map. So first let's fix the context. So let R be an R module. No, maybe. A commutative link with unity. VW be R modules. Okay, so the following are linear maps. So we have the zero map. So 0 from V to double V given by 0 of V equals 0. Okay. Why? Well, the sum of two vectors will, the result of the zero map will be 0, and when we add two zeros, we get 0. And here as well, this will be 0 and this will be 0. Identity map, identity from V to V. Why? Oh, we just have, here will be the identity of the sum will be the sum, and here the sum will stay the same. And here as well, we multiply a vector with a scalar, and the result will be the same. Okay. Something interesting. So any matrix acts as a linear map. So let me do this rigorously. So if V equals Rm and double equals to Rn for some m natural numbers, then, and A is a matrix, a matrix from n times n. Okay, let's make this n and this n. A is a matrix. We can multiply vectors from here to get vectors from here. Then the map, let's call it, I don't know, A. curly A from V to W, so from Rn to Rm, given by A of V equals A times V. So we take a vector and multiply by a matrix, n times n matrix multiplied by n vector becomes an m dimensional vector. So this is for OV in Rn is a linear map. So this is a linear map. Okay, the sentence is a little bit strange. The following are linear maps, and I here again say it's a linear map, but I want to stress that this thing here is a linear map. So A is a linear map. Okay. Some other example. Let's say V equals to W. It's the space of so this is the space of continuous functions from not yeah. So continuous functions. Okay, I hope I don't make some mistake. Just so we define f not the map I from V W I f equals the integral from, let's say, I of f of x is the integral 0 to x of f of t dt. So integration is a linear operator. So here f is continuous. So f is from C0. And x is number from 0 to 1. So the properties of integration say that it acts linearly. If you multiply this function by some coefficient term, they go outside. And if you add two functions and integrate them, you get the sum of integrals. This is if the input is continuous, the output will be differentiable. So I can make it stronger. In the other direction, I have differentiation. So it is a linear map integration. Integration E is a linear map. Okay, I will not write differentiation, but because I need to introduce C1 and so on. Not topic for here. Okay. Now let's define two very important spaces which a linear map induces. Let me commit different continuity. V W are R modules, and F is a linear map. The kernel of F is defined by is the null space. Last time I defined the null space of a matrix, but it can be generalized for any linear map. So the kernel of F is the set of all elements in all vectors in V such that f of V equals 0. That's 0 W. And the image of A of F, sorry, is defined by so this is the set of all vectors that are this form V in V, which is all the vectors in W. So this is the set of all vectors in W, which can be expressed by this, and again there are subspaces. So remark as for matrices, and the proofs are exactly the same, so I will not do them. The kernel of F is a subspace, a submodule of V, and the image of F is a submodule W, and F is a submodule of W. Let me give example with integration, no, with differentiation, but of polynomials. So this is much more general than matrices. Matrices are only for functions from Rn to Rm, and this is for all vectors, for all modules. For instance, let's give example. V equals W equals the space here, the space of square polynomials, x a plus a1, space of square polynomials, x a plus a1 x plus a2 x squared, where they are real numbers. A0, A1, A2 are real numbers. So these are the real vector space. V and W are real vector space. This is a real vector space. Okay. And define define D from V to V, D of polynomial F equals F prime. Where F is in. So this is a space of polynomials. And because a quadratic polynomial, when you differentiate it, you get again linear polynomial, which is in particular quadratic. In particular quadratic when this coefficient is 0. Okay. So I get a polynomial, for instance, d of 2 plus 4 plus 4x plus x squared is 4 plus 2x. This is what I have. Example. So what is the kernel of D? Which polynomials, which quadratic polynomials have derivative 0? Constant. Okay, kernel of D is the space of A0. So these are constants. And what is the image of D?
Just the set of linear polynomials.
Yes. Image of D is the set of linear polynomials. So it's A0 plus A1x. So these are linear polynomials. Why? Because always the degree goes down and any linear polynomial can be expressed by some derivative. We just integrate it somehow. Doesn't matter what is the preimage. Okay. Linear maps. Okay. Let's just prove some very simple proposition. I'm not sure I need it, but it's very basic. Consider a arc module. Sorry, yeah, I'll be a commutative unique unity. V and WB are modules. And we have a linear map. F is a linear map. Then F is injective. Does somebody know what's the characterization of injective linear maps? Do you know?
What do you mean by characterization?
Do you know equivalent property of linear map being injective?
Principle?
No, the kernel is 0. Its kernel is 0. Or this way. Okay. Okay, first in that direction. If it's injective, then kernel is 0. So f of x 0. So let f is injective. And we need to prove that the kernel of f is 0. We need to prove okay, so take, first of all, 0 is obviously in the kernel because f of 0 is 0. So since f of 0 equals to 0, then 0 belongs to the kernel of f. So that means that this thing here is in the opposite direction. So now let's take two elements of, let x belongs to the kernel of f, then f of x equals to 0 by definition, but also f of 0 equals to 0. Also f of 0 equals to 0. So we have f of x equals 0 and f of 0 equals to 0. And what we can conclude, yeah, because it's injective, since f it's injective. And so two things have the same result. F is injective and f of x equals f0, then x equals to 0. Okay. The opposite direction, okay, right. It's similar. Okay. I think we should finish here, maybe. Yeah, let's take a break and continue after the break.